To enhance your understanding of simple linear regression, we'll build on the example of brain size and IQ a little more deeply by investigating the sum of squares. Here are the data on brain size predicting IQ. And what we can do in this example is we can think about what is the null hypothesis for these data. If there's no relationship between brain size and IQ, what would you predict for a given brain's IQ? Well, I think you would just predict the average IQ. And that's the null hypothesis. The null hypothesis is, hey, I don't need a model, just plug in the average IQ. And then we can think about, is the model itself, I'll draw this line here is the model, is that model any better than just predicting the mean IQ? Sums of squares are an interesting way to think about this. Once we draw the line, which gets fit by the computer, the ordinary least squares, minimizing the sum of the squared residuals, we can start to partition out some of the variability. And what I mean by that is this. Let's play with some ink. I want to pull out a blue pen, and I want to think, imagine that you had to connect each point here to the mean of y. I take each point and connect it to the mean of y. In other words, I take each individual point and I see how far away it is from the middle. Now, some points are above and some points are below. So what we do is we square it, and this will turn everything positive. And I can almost get a measure, you can think of it conceptually, of how much blue ink do I need to use in order to connect all the points to the mean. If I do that and I add them up, this is what's known as the sum of squares total. The total sum of squares. How much variability is there? Well, we see this in the bottom table right here. If I did this, you can think of it, it's like I would need to use 20,000 amounts of blue ink to do this. It's how much variability there is. Look at this equation for the total sum of squares. Do you recognize that from anywhere? It's the top of our calculation for variance and for standard deviation. It's how far are the points from the mean, the total sum of squares. Now, what we can also do then is fit a line. So I'm going to pull out a green pen here, and I want you to think about the line of best fit and the idea that not every single point is exactly on the line. We fit this model, and the model misses for some people. We make a prediction, but the prediction isn't perfect. There's some leftover or some residual variability that's not captured by the model. And what we can do is we can take each individual point and we can see how far away that point is from the line. We need a new notation here. We're going to do a little caret or a little hat, and that is how far is each point from the line. Square those up and add them up, and we get a measure of sort of how much green ink did we use? How much variability is left over after we fit the model. In this bottom corner here, we can say that leftover is about 18,000. So it's interesting that we have a measure of how much variability there was, about 20,000. And then we fit a model and we said there's about 18,000 left over. I think you can visualize this by using the ink if you had to. For each point, let's look at this guy, this point that's up in the top right corner. You see how much blue ink we needed to use to connect him to the mean? How much ink do we need to use to connect him to the model? Not as much. We've explained some of the variability in IQ. How much have we explained? Well, we've explained some amount such that there was 20,000 units of variability to begin with, and now there's 18,000 left over after we fit the model. So how much did the model explain? Well, you think about this for a few minutes, you could do a little bit of math. 20 minus 18 equals about 2. And this is what's known as the model sum of squared. You take the total and you subtract the residual and you get the model. How much of the variability is explained by this model? There was about 20, and this model explained about 2. This leads to an interesting number, which is how much of the variability, what percent of the variability is explained by the model. 2 divided by 20, this is about 10%, right? And this is known as the R squared, the percent of variability that's explained by the model. And you see this over here in this table. There's about our 10%. It's around 11%. Another thing that we can do with this is we can think about, on the average, how far are the points from the line? Now, we know that the standard deviation sort of captures how far are the points from the mean, but now we can sort of capture how far are the points from the line. This has 2 names, this statistic. It's a little confusing. Sometimes it's called the standard error of the estimate, kind of like the standard deviation of the model. It also has the name the root MSE, the root mean square error. And the way we get this, if you look in the bottom table, we have model sum of squares, and then we have this residual sum of squares, which we said is sometimes called the error sum of squares. So in total, the points we said are about 18,000 green inks away from the line. And how many points do we have? Well, roughly, we have about 37 points. 18,000 divided by 37 would mean, on the average, the mean on the average, these points are about 500 away from the line. But remember, we squared it. We squared all of these. So that's why we take the root of that mean square error. So it's something like the square root of 499, and that number is right here. And this number answers, on the average, how far are the points from the line? Or what is the standard deviation around the regression line? Let's look through some slides that recap this information in a little more detail. So we saw that nice example of the sum of squares handout, which parsed out some of the variability. How much total variability is there? How much is left over after I fit the model? The difference must be how much the model explained. We can calculate the R squared, which is the percent of that total variability that's explained by the model. And then we can calculate the root MSE, which is the square root of this guy up here, the root of the mean square error. And that tells us, on the average, how far are the points from the line. The computer will calculate this for us with those equations that we used. How much of the total variability in the outcome is explained by X? Well, that's the number we saw called R squared. You take the model sum of squared, also known as the regression sum of squared, and you divide it by the total sum of squared. How close are the points to the line? Well, that's the standard error of the estimate, or the root of the mean square error. And it's the standard deviation around the regression line. These are 2 really important numbers that summarize how well the model fits or explains the data that we have. Now, there's an interesting little distinction on this slide. We have some quotes. We have to be careful not to imply any causality when we look at these data. At its heart, we still just have a bunch of dots and we're drawing lines through it. When you start to say the word modeling, you can confuse people and make them think you're able to say a little more than you actually can. R squared, again, what percent of the variability can be explained by brain size? The standard error of the estimate is plug in my brain, the size of my brain, and your IQ prediction will be plus or minus 22.4. We'll get more practice on these when we play with more simple linear regression models, And then when we build off this to the idea of multiple linear regression. Stay tuned.